looks like we're in business. Last time I started a little early, this time I start a little late. How about that? Let me see, and then is everything else working fine? That's all looking good. Okay. We can close that for now. Alright, so the continuation of what we started last time. Let's see. So there were some things that I had time to think about that I'd like to go over again. Well, mainly one thing. And as for that other problem, the one with the inscribed isosceles triangle, I haven't had the opportunity to look at it, plus I also kind of forgot about it until a few minutes ago, actually. But the one that has been on my mind, and it's probably because I did it towards the end, was the explanation of this cube thing. So that's actually what I want to start with before I do anything else today, because last time I knew this wasn't the correct description of how the approximation works, but that it was kind of, close enough to the truth that it gave you some intuition about why dv does not necessarily exactly match delta v. I attributed the difference to being the volumes of these corner cubes, and sometimes that's what happens, but I thought about it some more, and I came to realize why the 3s squared part made sense. I came to realize what the 3s squared business was all about. So that's actually what I'd like to do first. So let's restate the original problem. Actually, I need to find the original problem. I probably should have marked the page that I was at when I did all this. Probably should have marked where I stopped last time. Give me a minute to find it. It would be under... Where is it? Linearization. Oh, there it is. Page 183, it looks like. Okay, here it was. So it said, the edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube and the surface area of the cube. Let's have a look. So, of course, what I did last time was we drew the cube. We wrote that the equation for the volume of a cube is v equals s cubed. And we differentiated, we got dv equals 3s squared ds. Let's see, and our cube looked something like this. Okay. And we said the error ds equals delta s equals 0.1 centimeters, and s was 30 centimeters. And I'm not going to redo the problem, but for those who were curious about how this all works, this explanation is for you. Everybody else, I guess, can tune me out, but I'd prefer that you do have some curiosity about this. So, the example I was doing when I was trying to explain this last time, the example I was doing was, I think I was calculating what you subtract from the cube if you assumed that the length of the edge was overestimated and that it's actually too high by 0.1 centimeters. That's what I was going for. And actually, when I thought about it, there is a way to illustrate that, but my art skills aren't really all that good. So I think I would rather calculate the dV in the opposite direction. What if you're underestimating the volume of the cube? So what's the bigger volume that the cube should have? I think that would be easier to explain what's going on here. I might end up doing both, but let's start with that. So let's say that you want to calculate dV as the amount that you need to add to 30 cubed in order to get a larger volume. Let's suppose that the error was in that direction. So what is the 3s squared ds doing? Well, if s is the length of the edge of the cube, then s squared is the area of any one of the faces of the cube. So what we're doing here to estimate our error is we're adding s squared times ds, and we're doing it 3 times. So we're doing it on 3 faces of the cube. S squared times ds. ds is going to be a sort of thickness. I think it'll make more sense when I draw one of these. So let's say we stretch this edge out by 0.1 centimeters. Not to scale, of course. But let's say we stretch it out by 0.1 centimeters. What happens? Well, what we're doing here is we're adding a rectangular prism on top of this cube. A very thin rectangular prism, mind you, but a rectangular prism nonetheless. And what is the volume of that thin pink slice that I've put on top of our cube? Its volume is s squared, right, the area of the face that it's extending, times the thickness. This height, is ds. It's the 0.1 centimeters. So it's 0.1 centimeters times 30 squared is its volume. Okay, so where does the 3 come in? Well, the 3 comes in when you do this to 2 more faces. So, like so. Let's say I do this again here. Let's go ahead and connect these. So we've added that, and then we'll do it one more time for that front face. Okay, and let's do that. There we go. And then connect those, and then connect those. Okay, there we go. And now you can see why this is not a perfect estimate of the error. Let me actually shade these in. Now you can see why this is not going to give you the exact volume you would have gotten if you just did 30.1 cubed. because there's some missing parts. Over here. Actually, let's go ahead and draw in the missing parts that don't get caught in your dV. dV is just this pink volume, the volume of these three pink layers that I add on. If it were to be a perfect evaluation of the error, then it would also have to include, let's see if I can stretch it out. It would also have to include this bar, which we don't have, and it would have to include this bar, which we don't have, and it would have to include this bar over here. Let's see, stretch that and stretch that and do that. Yeah, it would also have to include that bar over there, which we don't have, and it would also have to include this corner, which we're missing. So that's why dV is not equal to delta V. But, you know, if ds is small enough in comparison to s, then the neglected volume of these three bars and that corner cube is small enough that you can probably get away with it. You can probably brush it off. Okay, what if the error was in the other direction? I have no clue how I'm going to be able to draw this, but I'll try. So we'll draw ourselves another cube. I know I'm probably spending more time than I should over just, you know, a concept that might not be considered necessary by most people, but I gotta finish what I started. So let's see, subtracting s squared 3 times. So these would be on the inside this time around. So let's see, we would have s squared ds. Did I say subtracting s squared 3 times? S squared ds 3 times. So we'd subtract, I would subtract that. So I would subtract that out, that whole layer. I would also, let's do this in a different color. Maybe that'll actually help me draw it better. We'll also subtract out another thin rectangular prism of volume s squared ds over here. And we would also subtract, let's do this one in navy blue. We'd also subtract that top slice. So over here, the problem is that, so in that first example, we weren't counting those 3 bars and that corner cube. In this case, the problem is that we're double counting and triple counting them. In this case, the reason that dV is different from delta V is that we're going to be double counting these bars and triple counting that corner cube. Let's see how that works. So if I shade the pink part, that first pink part that I drew that we needed to subtract. So you want to cut off that much, but you also want to cut off that thin prism over there, which already is overlapping with that first prism. So basically we're subtracting that pink bar twice. That pink bar includes, of course, our corner mini cube over there. So far that mini cube has been subtracted out twice, and this bar over here has been subtracted twice, or counted twice, I should say. Subtraction is what we do with it at the end. And then, of course, we're also subtracting off that layer, which overlaps with this, I guess we'll call it burgundy layer. So now that's been subtracted twice, including that corner cube. So that corner cube has been subtracted 3 times now, has been counted 3 times. This bar has been counted twice, that bar has been counted twice, and because of the overlap between navy blue and pink, that bar has also been counted twice. So you would actually have dV in this case would overestimate the amount you need to subtract from 30 cubed in order to get 29.9 cubed. Right? If you compare 30 cubed versus 29.9 cubed, and if you subtract those two versus 30 cubed minus whatever dV is going to turn out to be, then 30 cubed minus dV is going to give you something smaller. Hold on. No, I'm doing it wrong. 30 cubed minus dV is going to be, no, I'm on the right track. 30 cubed minus dV should give you something less than 29.9 cubed. And now that I'm looking at this, I think earlier I may have mistakenly said about this one that its volume would be 31 cubed if we underestimated it. That was a mistake on my part. It should have been 30.1 cubed. So yeah, if you heard me say that and were wondering what was up, I just made a mistake there. I said 31 when I should have said 30.1, but by now you're probably not even concerned about that, so I don't know why I am either. So yeah, that's a review of that problem, just understanding conceptually what the differential is doing. Hopefully that helped for those who really wanted to wrap their heads around it conceptually. Because yeah, your formula for dV should make sense. Whatever formula you get for your differential, it should make sense for whatever it is that you're actually working with. It should make some sort of sense why it's an estimate of the error. You just have to, spend some time staring at it and interpret the meaning of it. So where do I want to go now that I've cleared that one up? Let's see. Well, last time we talked about continuity, but we didn't really talk about the intermediate value theorem, so how about we do that first? The intermediate value theorem. What on earth does it have to do with continuity? And why does it even work? So suppose we have ourselves a continuous graph. Wow, that doesn't look very straight at all over there. Well, we'll ignore that side of it. Let's suppose we have ourselves a graph that's continuous. It doesn't necessarily have to be differentiable, so I'll make it piecewise like this. Suppose we have something like that. So intermediate value theorem says that if I have two given y values, let's say this one over here, and let's also say this one over here. If I have two given y values at two given points, let me do that in a different color. Let's say green. Then as long as the function is continuous between those 2 points, all y values between those two y values are guaranteed to occur. Why? Why does that make sense? What is the intuition behind it? Well, the intuition behind it is actually pretty simple. So if a function is continuous, that means you have to draw it without lifting the pen. So if between, we'll call this point A and we'll call this point B, x equals A and x equals B. If between the points corresponding to x equals A and x equals B, you have to get from here to here without ever lifting the pen, then there's really only 3 ways you could do it. One way you could do it is by going straight from this point to this point. So that's one route you could take. You could just go straight there, in which case you're passing through all the y values in between. Another way you could get there is you could go down and then back up eventually. So you could, well, that's what this graph is actually doing. It goes down and eventually comes back up. Now, it covers more y values than the ones in between. Let's call them, what should we call them? Let's call them h and k. It visits more y values than just the numbers between h and k. It visits all these numbers that are less than h, but that's okay. What's guaranteed is that all the numbers between h and k are visited at least once. So yeah, if you go down and then back up, then obviously you visit all the values in between. What if you go up and then back down? What if you go up and then back down? Same idea, so if I went up, eventually I'd have to come back down. No matter what I do, I'd have to eventually come back down in order to reach that point and close. And on my way down, on my way back down, I visit all of these y values which are between h and k. So that's the intuition behind the intermediate value theorem. If you understand it, you don't have to memorize much of anything. And as for using it, it's not really that hard. I mean, you've used it before, so you don't really need me to explain it, I don't think. But yeah, do we need an example for this? I don't think we do. Yeah, I don't think we need an example for this. Let's just move on. The question is, move on to what? Let me see what I can find for inspiration. How about... Oh, the mean value theorem, why not? Since we're talking about the intermediate value theorem, why not talk about the mean value theorem as well? So the mean value theorem kind of follows some similar reasoning to this, actually. It's just, really, it's the intermediate value theorem applied to derivatives. that's one way you could think about it. So mean value theorem, whoops, that's not a V. Mean value theorem is really just the intermediate value theorem applied to derivatives, though that might not be obvious from the way they normally teach it to you. So mean value theorem, suppose you have a graph that is differentiable between two given points. Let's mark our points A and B. And let's say the function is differentiable everywhere between those 2 points. Differentiable means continuous, of course, but it also means that the curve is smooth. It also means that the curve is smooth. Okay, so we've got f of a, which looks like it's there, and then f of b, which looks like it's here. So I'll call that f of a. That's probably what I should have called these earlier, actually, now that I think about it. And then that we will call f of b. F of b. Okay. So the mean value theorem tells us what? The mean value theorem tells us that the slope of the secant line between a and b is equal to the slope of the tangent line at least one point on the way from A to B. So if I go ahead and draw the secant line, which is going to be that line, so at some point the tangent of the graph is parallel to that green line. At some point between A and B, at least once. And in fact, I think it's going to actually happen twice the way I've drawn my graph. So let's see. I can actually spot it. One of them seems to be about there. That's parallel to the green. And the other spot seems to be about here. The other one seems to be about there. I drew that a little off so it doesn't look too parallel, but if you take my word for it. So how can we think about this so that we can remember it intuitively? How can we think about this so we remember it intuitively? Really, it's the same logic I presented here. There are three ways to smoothly get from point A to point B. One way is to just go straight from point A to point B, in which case you're on the green line, and on the green line, well, all points have a tangent line that's parallel to the green line. So that's one scenario. Another scenario is you go down and then up. If you go down and then up, if you're curving smoothly, then at some point, even if you start with your slope of the tangent line being below the green line, eventually you have to curve back up to reach point B, and on your way curving back up, you'll have a moment where you're parallel to that green line. And in fact, you'll also have to have a moment where you're going up faster than the green line to make up for that downward dip that happened in the beginning. And of course, if you go up and then down, then it's basically the same logic, just in reverse. If you have to go up and then down, then you start with a very high slope, and eventually your slope has to come down, and on its way down, at some point it'll be a tangent line parallel to that green line. So yeah, that's guaranteed to happen at least once, could happen multiple times. In fact, could happen an infinite number of times. That sentence didn't feel right. An infinite number of times. Could happen an infinite number of times if you just had a straight line along the way that's parallel to the secant line, if not the secant line itself. So yeah, that's the mean value theorem intuition. But there is another way you can look at this. If a function is differentiable between points A and B, that means that its first derivative is continuous. That means that its first derivative is continuous. And if its first derivative is continuous, then if you were to graph the first derivative of this, which I probably won't be able to do easily, then you could apply intermediate value theorem instead. So let me see, how would I interpret the slope of the secant line in that version of events? So slope of the secant line, if I take the derivative, the slope of the secant line would basically be the so the slope of the secant line would just be this difference right here, the difference between h and k in my earlier example of the intermediate value theorem. That's what the slope of the secant line would end up representing. The slope of the secant line would represent the value of k minus h, if I'm thinking about this correctly. Yeah, I'm not sure. I probably should have prepared a good illustrative example of this ahead of time. So much for going in without a plan. That only gets you so far. Let me see if I can think of something that'll better illustrate what I'm trying to say here. What if I did the graph of x cubed So if my original graph is the graph of x cubed, drawn somewhat poorly, and let's say I did it between -1 and 1. Let's say we did it between -1 and +1. Then the graph of its derivative would be the graph of 3x squared. Let's see if I can draw it lined up with this. So the graph of 3x squared would end up looking something like that. And so let's see, at 1, and at -1, the graph of 3x squared would have a y value of 3, a y value of 3. So that's x cubed, that's 3x squared. What would the slope of this secant line represent? Well, let's see, so it's from -1 to 1. Well, let's draw the secant line connecting those two. Should look like that. And it would have a slope of +1. So what does a slope of +1 represent in the derivative graph? I guess I'm about to learn something new myself here. Let's think about this a bit. -1, -1 comma -1 to +1 comma +1. It is a slope of 1, so I didn't mess up there. But what does that mean for this? I mean, I see where we could get a derivative of 1. It would just be somewhere around here, I guess, if this is at 3. If that's a 3, then a 1 would be a third of the way down, so somewhere around here. So, in fact, there are 2 points where 3x squared is equal to 1. X equal to positive or negative, I guess, square root of 1/3, it looks like. Just doing some quick mental math there. But where does the intermediate value theorem fit into this? How would I apply intermediate value theorem to this? I mean, I know there's a connection, this is one of those times where I'm reminded that my intuition about things has me take all these fantastical leaps of logic where I can make sense of something without necessarily, going through all the steps and proving that it makes sense. And that's where I have trouble teaching, because to me it's just some sort of, well, it's an intuitive process, so I don't have to think about it all that much. I just kind of imagine that it would work that way, and I'm satisfied with that. But when it comes to actually working it out, Well, I'll give this a few more minutes, and if I don't come up with anything, we'll just move on. Okay, I think I have it, though it probably still won't make much sense when I explain it. I'll have to mull it over some more and, refine my explanation of this, but I would say the slope of the secant line here represents the average derivative value here. It represents the average value of 3x squared between -1 and 1. So the average value has to be between the minimum and the maximum. So I guess you would apply intermediate value theorem between something below the average value and something above the average value. So say, for example, between here and here, I mean, it works, but it just doesn't feel like a complete explanation. Oh well, I'll skip over this for now. It's not entirely necessary, but there is a connection here. There is a connection between intermediate value theorem applied to the derivative being, what's the word I'm looking for? There's a connection between the intermediate value theorem applied to the graph of the derivative of a function and the mean value theorem applied to the original function, not its derivative. But I can't quite explain this connection in words yet, at least not in very clear words. But maybe I'll mull this over at some point and it'll just be added to my tutoring repertoire from next year on, hopefully. Because these are some of the kinds of things that I go over with my students in tutoring sessions, throughout the year. Maybe not so much now during review time, but definitely during the year. These are the kinds of things that I go over with them so that they can understand the material rather than have to memorize it, or at least reduce the amount of memorizing that they actually have to do. Okay, what do I want to do next then? Let's look around and see what else there is to cover here. We did related rates, we did optimization, which means that we kind of did maximum and minimum values. Oh, curve sketching guidelines. Let's actually talk about that. Let me see. Where's a good problem that we can base this off of. So So it looks like it might be this section. Yeah, I can't seem to find one, but I'll just make up my own, I guess. So they will have a problem where they just kind of describe the behavior of a function without really telling you anything about the function, and they will ask you to just kind of sketch it. So they'll tell you something like f of x has the following properties, has the following properties. So first it'll tell you, for example, that it is continuous and differentiable. Let's say it's continuous and differentiable. For all x, for all x. It'll also tell you that from negative infinity to infinity, or no, let's say from negative infinity to, say, negative 3, f prime of x is positive. And it'll tell you from, of course, negative 3 to positive infinity. It'll tell you f prime of x is negative. My handwriting feels off today. But maybe that's just how I'm seeing it. Anyway, it'll also tell you something like from negative infinity to, let's say, negative 5, the graph is concave up. Or actually, no, they'll say f double prime of x is positive. Or maybe they'll say it's concave up, who knows. Also, it'll be positive from, let's see, negative infinity to negative 5, and let's say also from 0 to infinity. It's also, it also has a positive second derivative. And then from negative 5 to 0, f double prime is negative. And then it'll tell you to sketch f of x. Sketch a graph. Sketch a graph that could be f of x. Or maybe it's a multiple choice and they have 4 different graphs and you have to figure out which one is the best fit. But let's say you have to do it from scratch because that's the harder problem. Sketch a graph that could be f of x, and there's more than one correct answer here. Sketch a graph that could be f of x. So here, what I tell students is to make sure they know what I call the 4 strokes. And I think I talked about this in last year's review streams as well, but it doesn't hurt to go over them again. So the 4 strokes are, increasing concave up, which looks like this, decreasing concave up, which looks like this, increasing concave down, which looks like this, and decreasing concave down, which looks like this. So you've got increasing versus decreasing, and concave up versus concave down. That's what you've got. So make sure you know those 4 strokes. Once you know what increasing concave up looks like versus increasing concave down, and so on, once you know those 4, you should be able to handle any problem like this just fine. So let's see what the graph of this thing would look like. And of course, they could give additional information here for you to make the graph even more precise. They could give you the y-intercept, for example, and you'd have to just actually graph that specific point and make sure your graph goes through that point. But, you know, this is the stuff that would trouble most people. The additional information, I think you'll be able to handle just fine if you have it. It just, if anything, the additional information is, it's easy, but it imposes a few more restrictions, and so you'd have to spend a little bit more time planning ahead how you want the graph to look to make sure it goes through all the points that it absolutely has to go through. But we don't have such restrictions in this example, so we won't worry about that too much. Let's see, so important x values to mark include -3 and -5 and 0. So let's do 1, 2, 3, 4, 5. So there's -5, that's -3. Those are important points to mark. And of course, 0 itself, which there's no point in marking. It's on the y-axis. Okay, so from -infinity to -3, it helps to draw some number lines. So that's what I'm going to do. I'm going to draw some number lines for the first and second derivatives, or, well, at least their signs. So f prime of x and f double prime of x. What are their signs, positive or negative, and where? So f prime of x is positive from -infinity to -3. Let's see, we want -3 and 0 and -5, not to scale. Yeah, this is definitely not to scale. I've drawn -3 closer to 0 than it is to -5. That's definitely not to scale. But yeah, let's see what our regions are. So -infinity to -3, the first derivative is positive. So positive everywhere here, and then negative everywhere after that. And probably 0 at -3, especially if it's going to be continuous and differentiable. It's not going to have a vertical asymptote or a point of discontinuity or a cusp or sharp turning point. So yeah, I guess it would have to be 0 at -3. So I guess you've got a maximum. You'd have to make sure to graph it to look like that. Okay, and then f double prime from -infinity to -5, it's positive. From -5 to 0, it is negative. And then from 0 to infinity, it goes back to being positive again. Okay, and here is where I divide this up into a bunch of different sections. So basically, anytime either one of these number lines changes sign, that's a section. So here, the second derivative changes sign, so we're going to do a section split at -5. Also at -3, that's where the first derivative changes from positive to negative. So a section split at -3. And at 0, the second derivative switches sign. So that's a section split. So we've got, it looks like 4 different sections. Let's see. Section 1, increasing concave up. That looks like this. So that's increasing concave up. Okay, then we have a section that's increasing concave down, so it switches to looking like this. Then over here, first derivative negative, second derivative negative, so that's decreasing concave down. That looks like this, which matches the shape we're supposed to be getting. We're supposed to be getting a maximum at -3, a relative maximum, maybe an absolute maximum. And at 0, it switches to decreasing concave up, which would look like this. Okay, so those are the 4 sections, what they're supposed to look like. So let's go ahead and draw a graph that actually fits that description. See if I can actually squeeze it in on this page. So first, it's increasing concave up, so looking something like this until it hits -5. That's where we have, I guess that's an inflection point where it switches to increasing concave down. Then at -3, it switches to decreasing, still concave down, so maybe something like this. And then it hits 0, and that's where we get, it looks like another point of inflection where it switches to decreasing concave up and never turns back. Maybe it approaches some horizontal asymptote, or maybe it turns up. So again, like I said before, there are multiple interpretations. You could go this way, you could just have it flatten out and get smoother as you go. There's a whole bunch of different ways you could draw a correct graph that fits this description. I'll go for this route. that's looking to be rather vertical, but there is no vertical asymptote here. This thing is continuous and differentiable for all x, so it'll pretty much behave like a polynomial. Oh yeah, on this side, I guess, it could, again, go to a horizontal asymptote, or it could curve up. Well, actually, wait. No, it couldn't, because, and come to think of it, this is wrong too, because it's concave up, but it's always decreasing, so yeah, never mind. Actually, it does just kind of asymptotically decrease. Or maybe it just continues going down like that. But definitely not this. Not this, and not this either. It'll never curve up on that right-hand side. On the left-hand side, it could never... Well, it's supposed to keep going up as you go to the right, which means it's supposed to keep going down as you go to the left, while still being concave up. So yeah, I guess on the left it would probably flatten out like this, approach some sort of horizontal asymptote, or maybe it would continue on something like that. But you have multiple options, is the point. You have multiple options. As long as you stick with these general shapes where they need to be, then you will likely get full points regardless of what you draw. So that's one of those problems. That's curve sketching. Let me move this thing out of the way. Let's see what else we can work on. Well, I guess it's time to do integrals. I don't have anything else to do concerning derivatives, at least not that I can think of right now. So yeah, it's off to integrals. It is integral and antiderivative time. So you'll definitely want to have certain antiderivatives memorized by just, doing your derivative rules in reverse. You have to have the antiderivatives of sine and cosine, and secant squared and cosecant squared, and secant tangent and cosecant cotangent. You have to have all those memorized. They're just obtained by doing the derivatives of sine, cosine, tangent, secant, cosecant, and cotangent in reverse. So you should know those 6 derivatives, reverse them to get the antiderivatives of the 6 that I just mentioned. Also, you're going to want to know, if you're doing Calc AB only and not Calc BC, then you will also need to remember the antiderivatives of the inverse trig functions. Oh! Wait. Then we have one more thing left to do for derivatives, which is derivatives of inverse functions. How could I forget? Okay, let's hold off on integration after all. Derivatives of inverse functions. Derivatives of inverse functions. I don't know why I'm writing a title here. Derivatives of inverse functions. Yeah, let's take a look at this. So what's the formula for the derivative of an inverse function? Well, let's say that f of x and g of x, let's say f of x and g of x are inverses of each other. Then that means you learned in pre-calculus that f of g of x equals g of f of x equals x. We'll just take that first part. So we'll take f of g of x equals x. And if you take the derivative of it, if I take the derivative on both sides, then derivative of f of g of x, that's just chain rule, f prime of g of x times g prime of x equals derivative of x is 1. And so, to solve for g prime of x, I would get g prime of x equals 1 over f prime of g of x. Your teacher might write this as f inverse prime of x equals 1 over f prime of f inverse of x. I don't like this because it creates the need for unnecessary parentheses. Right? It makes it harder to write everything. I prefer to just say g of x equals f inverse of x. So definitely write this down on your paper for the free response section on the AP exam if you're going to do this, so that the graders know what you're doing, that you're not just making up some new function g of x. So yeah, I would just say let g of x be f inverse of x and then do it this way. It's just easier to write, but that's me. So you can do whatever you want. If that makes more sense to you, then just make sure the graders know what you're doing so you don't miss out on points over graders being unable to interpret what you're trying to do. And if you prefer this method, if you're comfortable with this, then, well, I wouldn't call it a method, but you know, if you prefer this notation, that's what I'd call it. If you prefer this notation, then you can stick with it. So whatever your preference is. Okay, so that's the formula. Let's go ahead and actually apply this to, since I was reminded of this by the inverse trig functions, let's apply this to the inverse trig functions. Let's derive one of the derivative formulas for an inverse trig function. How about we derive, how about we get the derivative of inverse secant? Well, no, let's start with inverse tangent. Let's start with inverse tangent. So how do we get the derivative of inverse tangent, or arctangent is what some teachers will call it. Arctangent, inverse tangent. It doesn't really matter whichever one of these your teacher uses, or whichever one of these you use. More importantly, they're equivalent. I stick with this. I mean, I know the reason that this exists. The reason that you would call it arctangent is to avoid confusion, so that you don't interpret tan inverse as tan to the negative 1, which is 1 over tan, which is cotangent. So I get it, but at the same time, if this negative 1 meant tan to the negative 1, which meant cotangent, then why wouldn't I just write cotangent of x straight up, right? So I don't think there's really any confusion in using this. So that's what I'm going to use. So derivative of tan inverse of x. That's our task. Derivative of tan inverse of x. What is it? What is it? And not from memorization, though you will be expected to memorize them. You can actually just rederive it on the spot, if need be, if you don't have it memorized. And here's how you would go about doing that. So you would make use of your knowledge of the derivative of the tangent of x. You would say, so tan inverse of x, that's your g prime. So derivative of tan inverse of x, derivative of tan inverse of x equals 1 over tangent prime of tan inverse of x. Well, what's tangent prime? What's the derivative of tangent? That would be secant squared. So it's 1 over secant squared of tan inverse of x. And this is where people get stuck and they're not sure what to do. I mean, how do you even evaluate secant squared of tan inverse of x? I mean, if it was tan of tan inverse of x, that would be easy. That would just be x. But what about secant squared of tan inverse of x? What on earth is that supposed to be? So here, what you want to do, if you're doing Calc BC, definitely pay attention here because you need this for trig substitution later. But even if you're not in Calc BC, you'll want to know this. Draw a reference triangle. So let tan inverse of x be some unknown angle theta such that tan of theta equals x. Or better yet, let's write it as x over 1. Let's draw a triangle that illustrates this. So here's a right triangle. Here's the angle theta. And tan of theta is x over 1. So opposite over adjacent is x over 1. Well, what if the length of the opposite side is x and the length of the adjacent side is 1, for example? Or you could do 2x and 2, or x squared and x. It really doesn't matter as long as opposite over adjacent comes down to x over 1, but I use x and 1 because it's the easiest combination I can think of. It's the quickest one you could come up with. So let's go ahead and get the hypotenuse here. It would be the square root of 1 plus x squared. Okay, so tan inverse of x is theta, and we need to get secant squared of tan inverse of x. Secant squared of theta. What is secant squared of theta according to this triangle we just drew? What is secant squared of theta according to this triangle we drew? Let me switch colors here. So secant squared of theta, that would be, let's see, it would be 1 over cosine squared. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So hypotenuse over adjacent, square root of 1 plus x squared over 1, which is square root of 1 plus x squared. And then it's the secant squared. So it's that squared, so you just undo the square root. Secant squared is 1 plus x squared in this case. And there we have it. So that's where it comes from, 1 over 1 plus x squared. And if you have the derivative of inverse tangent memorized, then you recognize this as the correct derivative. Okay, now let's do it for, say, inverse secant. Let's do that as another exercise, just so we have another example to go with. What is the derivative of inverse secant of x? Well, it would equal 1 over secant prime of inverse secant of x according to our inverse function derivative rule. And of course secant prime is secant tangent, so it would be 1 over secant of secant inverse of x times tangent of secant inverse of x. Okay, secant of secant inverse of x, that's easy. That's just x. So that's 1 over, that's just going to be x. And then tan of secant inverse of x, that's the part that we're going to need to put some more time into. So secant inverse of x, let that be theta, such that secant of theta is equal to x, or preferably, I like to write them as fractions, x over 1. That helps with drawing our reference triangle. So, reference triangle, if this angle here is theta, then secant, so hypotenuse over adjacent is x over 1. Okay, that means that this opposite side would be square root of x squared minus 1. So then tan of secant inverse of x is tan of what we called theta. And tan of theta, according to this triangle, is square root of x squared minus 1 over 1. So square root of x squared minus 1 over 1 is just square root of x squared minus 1. And there we have it. I think in the version you have to memorize there's an absolute value here, and the reason for that, I believe, has to do with the domain restrictions, or no, not the domain restrictions, the range restrictions on the secant inverse function, if I'm not mistaken. Let me think, because secant inverse would have the same range restrictions as cosine inverse, since the two are related, and cosine inverse can only give you values from 0 to pi, which are all positive. So then secant of something from 0 to pi, you can definitely still get the negative secant values there, because you can because secant of anything from pi over 2 to pi would be negative, so you can still get negatives there, but tangent of anything from pi over 2 to pi would also be negative, so you'd get a negative times a negative, which is a positive, and then from 0 to pi over 2, both the secant and the tangent would be positive. Okay, so that's why the absolute value is there. So that's why the absolute value bars are there. Because, yeah, when you multiply these, you have to get a positive. And because the square root function, by default, you take the positive root, that means you have to make sure that this x is also positive. Okay, so that's the reason for it. It's all about range restrictions. Okay, I'm glad I remembered to actually go over this. Now we can go back to what got us on this tangent in the first place. Well, I wouldn't call it a tangent. I mean, it was, I'd argue, necessary to cover this, but now we can go back to integrals and antiderivatives. What do I want to do with integrals? Let's take a look at where the book starts and see what I want to do. Okay, so they start with Riemann sums. Okay, sure, why not? Let's take a look at Riemann sums. What do I want to do with Riemann sums? Something that you wouldn't have learned already, or something that is typically not taught all that clearly. I can't think of anything really. The only thing I have to say right off the top of my head that I can think of saying when it comes to Riemann sums is a lot of students forget to think in terms of Riemann sums, and that comes back to bite you in later sections, like when you're doing disks and washers, for example. Those are Riemann sums. When you're doing, what else do you do that involves Riemann sums? I'm trying to think of something for the BC Calc students. Cylindrical shells, which are kind of in the same vein as disks and washers. And then the physics students, the AP Physics C students, when you're doing your moment of inertia and Gauss's law calculations there, those are places where you would use Riemann sums to help interpret and put together like what you need to integrate in the first place. So yeah, I'm really not sure what else to say about Riemann sums, what would be worthwhile to cover. Yeah, just remember to think in terms of them, really. Just remember to think in terms of Riemann sums when you're using integration for purposes other than calculating area under the curve. When you're using integrals to calculate volumes and in physics densities and masses and charges. Yeah, I think I will pass on Riemann sums for now. Maybe if I think of something later that makes them worthwhile, then we'll go back and revisit them. Definite integrals, and I guess interpreting integrals. Let's see, what do we want to do here, if anything? Well, the AP exam definitely likes to give you a bunch of problems where they'll present you with a graph. And they won't tell you what the function is, but they'll give you a graph, say, that looks like, what do I want to draw here? Simple geometric figures. They might give you a graph that looks like this, then goes around, say, in a quarter circle like this. Then goes up to here, for example. Okay, let's say this is at x equals, let's say this is at x equals 2. So if that's 2, then I guess, yeah, we can say that's at 4. And we can say that that is at y equals 1. So I'll say that's a 1. We'll say this is at 2. It would have to be if this is a circular piece. And then here, let's say that's at, that's not really -2, is it? Let's say that's -1.5. And then let's say that's, well, that's twice as far. So let's say that's, but do I want it to be twice as far? No, I don't. Let's say that's -2. Let's disregard the scaling as we've been doing. So what can we do here? What can we do here for a problem? They'll give you something like, they'll tell you something like this is a graph of f prime. And they'll tell you, for example, that f of 2 equals some number, let's say 7. And they will ask you to come up with f of -1.5 and f of -2 and f of 4 and I guess f of 0. So that's something they could ask you. I'm not going to do all of these, but I'll do I'll do f of 4. I'll do f of 4. And I will do, let's do f of negative 1.5. Let's do those two. And you can do the others for additional practice if you want, but I'll do those two. So f of 4 and f of negative 1.5. So f of 4, what I really want to do is take advantage of f of 2. So there are a couple of different ways you could go about this. One way is to think of the integral from 2 to 4 as the net change in f between 2 and 4. Another way you could go about this is you could use the fundamental theorem of calculus. So you could either go net change theorem or fundamental theorem of calculus on this. I'll do one of each. So which one do I want to do first? Let's do f of negative 1.5. Let's use fundamental theorem of calculus for this one. So f of negative 1.5. Let's see how I would go about calculating it. So the fundamental theorem of calculus would tell us that the integral from, I want to do negative 1.5 to 2. The fundamental theorem of calculus tells us that the integral from negative 1.5 to 2 of f prime of x with respect to x is equal to f of 2 minus f of negative 1.5. The fundamental theorem of calculus defines the definite integral, basically. Okay, f of 2 we know because it's given to us, it's 7. F of negative 1.5 is what we're trying to find out. And the integral we can calculate from negative 1.5 to 2. The integral is just the area under the curve. So it's this area of this triangle plus this quarter circle. So let's go ahead and calculate those areas. So for the triangle, 1/2 base times height. Height is negative, or base, I should say, is 1.5 units wide times height is 2, and then times 1/2. So half of 2 is 1. 1 times 1.5 is 1.5. It's positive area because it's above the x-axis. So that's positive 1.5 for the triangle, plus the area of the circle, or a quarter circle I should say, is 1/4 of the area of a full circle of radius 2. So area of a full circle of radius 2 would be pi r squared, pi times 2 squared, so that's pi times 4, and then 1/4 of that, because it's a quarter circle, 1/4 of pi times 4 is just pi. So 1.5 plus pi. I didn't plan it out that way, but it looks nice, so glad it turned out to actually be a nice looking sum. Okay, and the rest is just solving for f of negative 1.5. You know how to do that. It's just simple algebra. I would add f of negative 1.5 over to the left side to get rid of the negative sign, and then subtract these over to the right. Don't plug in the value of pi, just leave it as, well, I would do 7 minus 1.5, whatever that is, and then that minus pi, and I would leave that as my answer. So that's for f of negative 1.5 using the fundamental theorem of calculus. F of 4 using the net change theorem, which isn't all too different really. the net change theorem says that the integral of f prime from one point to another point, from 2 to 4 in this case, is equal to the net change in f of x from 2 to 4, is equal to delta f from 2 to 4, basically. So let me do this in a different color. Let's say navy blue. Yeah, even though the lighting outside doesn't look too good coming in from the window, it still looks pretty good on screen. Alright, so where was I? Right, so we were doing integral from 2 to 4 of f prime of x dx equals delta f of x. It's just another way of looking at it, is the net change in f of x, the total change, whether it's gain or loss. If it's negative, it's loss. If it's positive, it's gain. In this case, it will be a positive area. So from 2 to 4, let's see, and it's got a height of 1, so 1/2 base times height. 1/2 of the distance from 2 to 4 is half of 2, which is 1, times height is 1. 1 times 1 is 1, so the area is 1. So we've got 1 equals the change in f of x, and that's from 2 to 4. So it equals the same thing you would get using the fundamental theorem of calculus, f of 4 minus f of 2. So f of 4 minus f of 2, which we know to be 7, equals 1. Add the 7, f of 4 equals 8. And there we go. So the two ideas are not too different from one another, really. At the end of the day, you still end up going through the same series of calculations. It's just, you know, two different ways of thinking about it. But it's important to be aware of the net change theorem regardless. It's something that teachers don't really emphasize all that much, if you ask me, though they should. Net change theorem is important to understand, at least conceptually, if you're not going to apply it to the problem. If you're satisfied with fundamental theorem of calculus, then go right ahead, but don't skip on understanding the concept of the net change theorem, because the integral of a derivative does not actually give you back the function that it's a derivative of. It gives you the change in that function, which then needs to be added to or subtracted from something in order to provide the original function that this integrand was a derivative of. And in case this is your first time hearing me use the word integrand, that's the word for the thing inside the integral symbol. This is called an integrand. This is called an integrand. Coincidentally, I should mention, whatever's inside of a square root, whatever's inside of a radical symbol is called a radicand. If you're adding two numbers, so a number and another number, these numbers are called addends. And that might feel like, extra information that you don't need to know, but trust me, it makes it very, very easy to communicate about these things. It's easier for me to explain things when I can, instead of calling it the stuff inside the integral every single time, if I just say integrand, then everybody gets what I'm talking about, assuming they've learned the word. And it just allows communication to go by much smoother. First of all, it's faster, but also more importantly, it's clearer. Because when I say stuff inside the integral, does that include the dx or does it not? Some people might misinterpret that. So yeah, it helps with efficiency and accuracy. Efficiency and accuracy. Okay, where do we go from here? Okay, what about taking the integrals of derivatives and taking the derivatives of integrals? I mean, we already did integrals of a derivative. What about taking the derivative of an integral? How does that work? It's not simple inversion. Let's see. What's an example that we can start with? What do I have here? So I guess we'll start with a misleading example that often gets students headed down the wrong road. If we're given g of x equals the integral from 1 to x of 1 over t cubed plus 1 dx, and you're asked to find g prime of x, and you're asked what's g prime of x. This one would just give you 1 over x cubed plus 1. And this might give you the idea that when you take the derivative of the integral, you just get the integrand, which is not necessarily correct. It depends on the integration bounds. It depends on what the integration bounds are. So let's take a look at some counterexamples and the idea will become more clear. I mean, it's not like you haven't done this before at this point in the school year, but you may have forgotten. It's one of those things that you don't do often, so it's easy to forget it. Let's see. What can I pick? What can I pick? Trying to pick one that illustrates the point without being too hard or too easy. Maybe I'll just make up my own. Okay, let's do this one. So, integral from 0 to x to the 4th of cosine of theta d theta. And let's say we want to take the derivative of this with respect to x. Over here, it's not simply going to become cosine of x to the fourth. Why? So if we go ahead and solve the integral part, we'll save the derivative for later. We'll save the differentiation step for later. But if we go ahead and integrate, what do we get? So we would get the antiderivative of cosine is sine, so it's sine of theta evaluated from x to the 4, or from 0 to x to the 4th power. So that's going to be sine of x to the 4th minus sine of 0. Okay, sine of 0 is 0, but even if it wasn't, if it was some other constant value, no problem, because the derivative of any constant is 0 anyway. So if we go ahead and take the derivative, that part is 0 and its derivative is also 0. The derivative of sine is cosine x to the 4th times, because of the chain rule, times 4x cubed, the derivative of x to the 4th. Okay, so that's a case where the top bound is some function of x. What about when the top and bottom bounds are functions of x? So what if I do, let's pick one from here. Don't see any good ones here. How about we do e to the x? No, let's call it e to the u. Yeah, let's call it e to the u. So let's do integral of e to the u du from, let's see, let's do it from sine of x to x to the 5th power. Okay, antiderivative of e to the u is e to the u, evaluated from sine of x to x to the 5, so that's e to the, oh, and I forgot, we're taking the derivative of this. So derivative of, yeah, let's do it on a, let's do it here. Derivative of e to the x to the 5th minus e to the sine of x gives us, of course, e to the x to the 5 times, by the chain rule, 5x to the 4, so that's 5x to the 4th e to the x to the 5th minus, let's see, that was e to the sine of x. I guess it got smudged as the ink spread out. Gives us e to the sine of x times the derivative of sine of x, which is cosine of x. And there we go. So what is happening here, I guess if you wanted to summarize the process, when you're taking the derivative of an integral, what you're doing is you're rewriting the integrand potentially twice. And each time you write the integrand, you also insert the integration bound that goes with it, the top bound for this one, the bottom bound for the other one. And you're also multiplying by the derivative of the top bound or bottom bound. So let's see if we can take advantage of that pattern to work with something that we wouldn't be able to easily integrate. Let's see how we would handle... Actually, I don't need a new sheet. I have some space here. Don't need a new sheet just yet. Let's see how we would handle something like integral, the derivative of the integral from 2x to x squared of, they have u squared minus 1 over u squared plus 1 du. This doesn't look very easy to integrate. In fact, I don't know if Calc AB has the techniques to integrate this. Let me see. So if you... Yeah, I think this requires integration by partial fractions, which is for Calc BC not included in Calc AB last I checked. So yeah, for this right now, I mean, even if you knew that technique, it would still take a while. So that's why I highlighted the pattern earlier for us to take advantage of. So we have potentially two terms here. So you've got u squared minus 1 over u squared plus 1 with the x squared substituted in for u. X squared squared is x to the fourth, so x to the fourth minus 1 over x to the fourth plus 1 times the derivative of x squared, which is 2x. So that's for the upper bound part. For the lower bound part, we've got replace u with 2x, so u squared becomes 4x squared minus 1 over 4x squared plus 1 times the derivative of 2x, which is 2. And there we go. That does it. Okay, what about this one? What if I did the integral from, well, the derivative of the integral of e to the sine of the natural log of x to the fifth. Let's say, oh, wait, not dx. Oh, well. I mean, yeah, let's say that's u to the fifth, and let's say that's du. Let's pretend. I mean, it's not something you have to worry about, but technically it's wrong. It's something that math professors get angry about. I wouldn't worry about it too much, but yeah, the variable the variable that you're differentiating with respect to ought to be different from the variable that you're integrating with respect to over here. It's just a technicality that math professors worry about. It has something to do with definitions and whatnot. Physics professors are far less concerned about that stuff, though, so you know, if you're trying to figure out who's the cooler group to hang out with. It's the physicists. Anyway, integration bounds. That's right. I was missing my integration bounds. So let's say it's from A to B, where A and B are constants. What's this going to be? This one's a trick question. This is going to be 0. It doesn't matter what the integrand is. If both your integration bounds are constants, then both of the two terms that you get here when you apply the fundamental theorem of calculus, it's going to be a constant minus a constant, and the derivative of that is the derivative of a constant, which is 0. So yeah, the derivative of any constant bounded integral is going to be 0. Just something to remember. That's probably going to be a multiple choice question, one that you can do very, very quickly if you keep this in mind. Okay, so that's derivatives of integrals. What else can we go over? Well, of course, U substitution. I mean, by this point, I would imagine most of you have done enough U substitution that you don't really need me to go over it and explain how it works. But there is something when it comes to U substitution that I would like to go over if I can find an example of it. Actually, let me see. Did I save that one problem set? Let me see if I have it in a file. Oh, yes, I did think to save it. Good. I think this is the one. Perfect. So there is this thing that you rarely have to do with U substitution. I guess some people call it back substitution, which is definitely worth looking at. So let's look for some examples that use that. Let me see, where are those problems? Here they are. So let's say we wanted to, it'll become more clear after you see the first example. Let's say you wanted to do the integral of 3 minus x to the 10th power with respect to x, an indefinite integral. How would you go about doing this? I mean, I guess you could FOIL. That doesn't look like it's going to be very quick. It doesn't look like it'll end painlessly, that's for sure. But you could do that. That is the option of last resort. But there is an easier way using U substitution. So what you would do here is you would do U equals 3 minus x and du equals negative 1 dx, or negative dx, whatever you prefer, if you don't like to explicitly write the 1. I mean, I usually don't write it explicitly, but for teaching purposes, sometimes I do. And then depending on which way your teacher had you go about this, from here you would either divide by negative 1 and say dx equals du over negative 1, and then substitute that in for dx here. Or the other method, which you'll probably see in college that math professors like to use, is you create a -1 dx in the integral so that you can replace it with a du. I don't have a -1 dx here, but I can make one because I can multiply by -1 and divide by -1. If I multiply this by -1 over -1, then I haven't really changed it, but now I have a -1 dx that I can take and replace with du. And I'm left with, I guess, it becomes integral of that other -1 that we didn't take. The one in the denominator just makes a negative up front. 3 minus x becomes u. Oh, actually, this one doesn't. This one is not an example of what I'm trying to do. At least it doesn't look like it. No, it's not. Okay, so let me reread and see where I went wrong. Yeah, that doesn't require use of that back substitution technique. Let me look through the file again and see. Ah, here we go. Okay. Here we go. Yeah, let's scrap this. This one's easy enough. You could finish the rest on your own. Okay, I've got one. So we've got integral of x plus 3 times x minus 1 to the 5th dx. Okay, how would we integrate this using U substitution? So I would want to get a u to the 5th here. So I would do u equals x minus 1. And then du equals, well, derivative of x minus 1, derivative of x is 1 dx, or just dx, and derivative of -1 is nothing. So I would get integral of x plus 3 times u to the 5th, and the dx just gets replaced with a du. What do we do with that x plus 3? Well, what you can do is you can solve for x in terms of u. Sometimes this is what you have to do. So take your u equals x minus 1 and solve it for x. So you get x equals u plus 1. And then if I replace this x with u plus 1, then I've got integral of u plus 1 plus 3, so u plus 4 times u to the 5th du, and you can distribute u to the 5th over that, so you get integral of u to the 6 plus 4 u to the 5th du, and the rest integrates the usual way from there. I don't think I will work out the rest of that. You know what to do from there. You've been doing this for quite a while, I would imagine, at this point in the year. Let's take a look at another one. Let's take a look at another case where you might have to do this back substitution thing. Let me check and make sure everything's in view. Yes, it is, though slightly tilted. Okay, let me see, what was that other example they had? So, integral of x square root of 4 minus x dx. Okay, here you would do u equals 4 minus x, du equals negative dx. So that just gives us integral of, we'll have a negative sign. The dx would get replaced with a du, and you've got x and square root of u. We can rewrite x as, let's see. So I would add x to the left and subtract u to the right using this. So I would get x equals 4 minus u. So we've got integral of negative 4 minus u times the square root of u, which I will rewrite as u to the 1/2 du. Distribute the negative, distribute u to the half, and you have integral of negative 4 u to the 1/2 plus, let's see, that's u to the 1 times u to the half is u to the 3/2 du, and the rest from there is your traditional power rule, followed by substituting back in for u, rewriting in terms of x. Okay, let's take a look at one more. Oh, this one looks intimidating, which of course means we should do it. So we've got integral of 3 plus natural log of x squared times 2 minus natural log of x over 4x dx. Oh my. What should we choose for u? I'm gonna try the 2 minus natural log of x first. U equals 2 minus natural log of x. That would give us du equals negative 1 over x dx. So that's negative 1 over x dx, which I guess would take care of the x in the denominator there. So yeah, I would just multiply by negative 1 over negative 1, and I'd have a negative 1 over x to take out. And then that would leave us with 3 plus ln of x, quantity squared, times u, over, I guess that would become a negative 4 du. 3 plus natural log of x. Well, I guess we could solve for natural log of x from here. And get, let's see, add natural log of x to the left, subtract u from the right, or what am I saying? Subtract u to the right. So we would get ln of x equals 2 minus u. Does that work? Yeah, I suppose it does. I think that choosing u equals 3 plus ln of x would have been easier, though, because this means we're going to have to end up foiling, which isn't too bad. It's squared, so, you know, we can foil it pretty quickly, but still, it would have been quicker if this had been the u squared and this had been the thing that we had to solve for. But it looks like you could have gone about this either way, is what I'm concluding from this. Okay, so 2 minus u. So 3 plus 2 minus u is 5 minus u. So yeah, we get, let's see, we get a negative sign from there. I'll leave the negative on the outside. And then you've got, what did we say? 3 plus ln of x is 3 plus 2 minus u. So 5 minus u squared times 2 minus ln of x, that's u, over, we keep the 4, and we got a du. And yeah, FOIL 5 minus u squared, distribute u over that, and I guess you can factor out the 1 over 4, pull it out of the integral. That's what I would do just to keep things, you know, clean and organized. And the rest is just power rule from there and resubstitute back in for u. Okay, so there we go. That's back substitution. You rarely have to use it, but remember that it's there. If you try u substitution and you're still getting stuck with x's that you're failing to rewrite in terms of u, or in this case, natural logs of x's that you're failing to rewrite in terms of u, then consider back substitution. Just remember that that's an option. Okay, where do I want to go from here? Areas between curves, I think, are simple enough. But let's go over them conceptually to make sure we understand them. So yeah, now we're in the integral applications chapter, and with integral applications, I find that most students have trouble just with the setup, and I think part of the reason is what I alluded to earlier when I was talking about Riemann sums, is that we forget to think in terms of Riemann sums, but also the other thing is we just tend to memorize the integral formats without really understanding them, and that leaves students not knowing what to do when they're presented with unusual scenarios, or even the usual scenarios. Sometimes they don't know how to, you know, like what's the correct direction of integration, or how do I switch things around when I'm integrating with respect to y instead of integrating with respect to x, and so on. So let's have a look at these. We've got areas between curves. So if I have two curves between points A and B, let's say curve 1 is f of x and curve 2 is g of x. Let's draw them in a different color. So let's say that's f of x. So that's f of x. And g of x, let's say, is this. So that's going to be g of x. And I want to figure out the area between those two curves. I want to figure out the area that falls between these curves like so. Okay, so it's going to be the area between curves, area between is going to be equal to the integral of f of x minus g of x dx. And why does this make sense? Well, you learned some rules about integrals, like the fact that this can be split into integral of f of x dx minus integral of g of x dx. Oh, and by the way, the area between curves is always an absolute value. That's something to remember. So, where was I before I mentioned that little side note? Right, so you can see that it's the difference of these two integrals, and that makes sense if you try and illustrate it here geometrically. The area under f of x, well, I should say the integral of f of x is the area between f of x and the x-axis. So it's going to be all of this area that I'm highlighting in pink. Okay, and the area under g of x, or I should say the area between g of x and the x-axis, is this stuff in green over here and over here and in here. So if I do integral of f of x minus integral of g of x, why does that give me the area between the curves? Let me go ahead and look at this piece by piece. So over here for this part, I'll divide this into 3 sections so that we can think about them individually. So in this first section, the integral of f of x is the area under f of x. It's the pink area. The area under g of x is the green. Area under f of x minus area under g of x, pink minus green. The pink includes what's also in the green, by the way. There's overlap between pink and green. So you're taking all of this pink area minus that little bit that overlaps, and you're getting this, which is directly between the orange curve and the yellow curve. I don't even know if you can still see the yellow curve all that clearly anymore. It looks better on the screen than it does to me on the paper. Kind of like what I was saying last time about the behavior of the yellow marker. Well, technically it's a Sharpie, but I call it a marker all the same. Okay, what about this second region? So in this second region, it's not a positive area minus another overlapping positive area. In this case, there is no overlap. In this case, it's positive area minus negative area. So these add up. And if I add the pink area and the green area, I get still an area that's between the yellow curve and the orange curve. An area that's between f of x and g of x. So it still works. It doesn't matter if both of the curves are above the x-axis, or one is above and one is below, or if both are below. It doesn't matter. You're always going to get an absolute value, a positive value for the area between curves, provided, of course, that you set things up correctly. Okay, and for this third region, I guess I covered up the pink parts down here with the green, but part of the area that's shaded green here was also shaded pink. So that section is an overlap section, so the integral of f of x would give you all of that minus the integral of g of x minus the green would give you just that, the stuff that's above the yellow and under the orange. So yeah, the formula for the area between curves does actually make sense. You can think of it as just one integral minus another integral. Now, what about if I was doing this sideways? What if I was doing it in terms of y? So let's draw let's draw I'll do a curve that looks like this, and one that looks like this, for example. And that'll be my f of y, and that'll be my g of y. Now, something that a lot of students have trouble with here is they forget the order of subtraction. The good news is, even if you forget the order of subtraction, that just means you're going to get a negative where you should have gotten a positive. So just take the absolute value of what you get and you'll get the correct area. But still, it helps to understand why it's right minus left as opposed to left minus right. Really, you should think of it in terms of higher values minus lower values. Over here, the areas, you can think of them, if you think of them in terms of Riemann sums. So let me draw two curves like this and say I'm calculating the area between them vertically. I'm doing Riemann sums. When you're doing f of x minus g of x, what you're doing is you're taking the upper y value minus the lower y value, and you're using that as the height of your rectangle, multiplied by a very small width of dx, adding all those up for all the values from a to b, and then you're getting your area between the curves that way. So it's the higher value minus the lower value. The higher y minus the lower y would give you a positive height. Well, same thing here, except your rectangles are going to be stacking horizontally like this. Stacking horizontally? Well, I guess technically we're stacking them vertically, but they're sitting horizontally is what I would say, but now we're getting too technical. So yeah, now your rectangles are horizontal, so their quote-unquote heights, now you've laid them sideways, so really they're widths, but this thing that you're trying to measure so that you can multiply it by the small changes in y, dy, these, in order for them to be positive, you need to take the greater x value minus the smaller x value. And that's how you remember it's right minus left. The further to the right, the greater the x value. So of course you would pick what's further to the right minus what's more to the left. And yeah, that's it. So the rest is pretty much the same. So it would be integral of, in this case, f of y is to the right, so right minus left dy. And there you go. So that's it. The rest is, well, depends on which functions you're getting. But the setup is usually the part that trips people up, understanding how to set it up. Now, what if they don't give you integration bounds? What if they don't give you a and b? So what if they give you two functions like so? So here's one function, and maybe they give you its equation, and then here's another function and they give you its equation. And they tell you what's the area between these two curves. What they mean is what's the area that gets caught in between them. So they mean this. I'm sure you've seen this before, but you know, I'm just kind of, I'm talking about this the way I'm used to talking about it, which is presenting it as if it were the first time. Even though I said in part 1 of this review stream, I don't want it to become this sort of full-on lecture where it's like I'm teaching it for the first time. I still can't break some of my old habits, it seems. So yeah, for these, you would just want to figure out where these intersections happen. Wherever two curves intersect, that means that at those intersection points, they have the same x's and the same y's. So all you have to do is set them equal to each other, set their y's equal to each other to find the x's at which they have those y's. So if, I guess I'll call this one f of x, and I'll call this one g of x. So yeah, wherever f of x is equal to g of x, so that establishes the y being equal to the y, say at this point or at this point, you should be getting two different solutions since there's two different points to find. Solve for the two possible x's, then plug those back in, solve for the two y's that go with them, or don't, depending on whether or not you need the y values. And yeah, there you go. If you're given a more complicated graph, if you're given a more complicated function, then that's probably a calculator problem. So make sure you know how to use the intersection feature on your graphing calculator. Make sure you know how to take advantage of your calculator's functions. But yeah, you find the intersection points and there's your integration bounds. If you were told specifically to do this one by integrating with respect to y, this would be quite the nasty problem to do with respect to y, because with respect to y, you'd be doing strips laid out horizontally. And so you would have to define a whole bunch of different right and left functions if you did it this way. So let's see what we have. So over here, you've got one problem, one subset of this problem. Then you've got, I'll say, yeah, that should do it. So I'll draw some more rectangles here. I can barely even see those, but I guess they're showing up well enough on the screen. Yeah, I don't know why they include yellow in these packs. It still bugs me, but you know, I don't like wasting things, so might as well use it. What color am I not using yet? Let's go with green. So if you had to do this in terms of y, the problem is you'd have to split it into 3 parts because the right function and left function keep changing as you move from one part to another part. For this top section, the function that's to the right is the pink curve. It's g of x. Well, it's the right half of g of x. And the function to the left is also g of x. It's the left half of g of x. So you would actually have to, well, you'd have to write the 2 possible inverse functions of g of x. So I guess we'll call them g inverse right and g inverse left. And so that would be one part of your integral. So g inverse right of y minus g inverse left of y dy. That would be the first part of your integral. No, that would be your first integral of 3 that you need to calculate the total area. And then your second integral, so that's what I've done in yellow. So that one, the rightward bound is the pink curve, so that would be g inverse right of y minus, to the left in the yellow section is the left side of the inverse of f of x, the navy blue curve. So that's going to be f inverse left of y and then dy, and then plus your final integral would be the green. And in the green region, your right curve is your navy blue curve, but so is your left. So that's going to be, oops, forgot that sign there, f inverse right of y minus f inverse left. I'm running out of space. dy. So yeah, this would be better to integrate vertically. But how would, if we, well, hold on, integrate vertically? No, this would be better to integrate with horizontal stacking, so in terms of x is what I'm trying to say. But if we had to do it this way, is it even possible to come up with 2 inverse functions for a function? Yes, it is, absolutely. So what if I had, let's do a simple one, f of x equals x squared. F of x equals x squared. It's got 2 inverse functions. One of its inverse functions is f of x equals square root of x. What's the other one? It's f of x equals negative square root of x. I should say f inverse of x here. Well, actually, no. I don't even want to write them like this. What I want to do is write them as f inverse of y equals square root of y, and f inverse, I'll call this f inverse right, and f inverse left is going to be negative square root of y. So yeah, there you go. So x equals positive square root of y, that would be this part. And x equals negative square root of y, that would be this part right here. So it is possible, and not always though, it's not always possible to do this, but it is at least sometimes possible to come up with two inverse functions for a function like this, which doesn't pass the horizontal line test, which is really the source of the problem here. Right? You learned about the horizontal line test when inverting functions, that if a function doesn't pass the horizontal line test, then it doesn't truly have an inverse unless you restrict it to just a section that does pass the horizontal line test. But now I'm rambling. There is a situation where you absolutely have to do this whole integral splitting business, which is when you have a region that is neither simple when integrated in terms of x nor in terms of y. So let me see, what would the shape of the curve be for a scenario like that? Or I should say the combination of curves. So if you had something that looked like, I can't really think of anything. Give me a minute here. There might be an example of this in the book. No, I don't see one. I'll just have to come up with one then. Think. So I'll start with one curve. Let's say this. And then what can I do here? So I can what if I came up with, I don't even know if this will work, but I have to draw it first so I can look at it and see. No, what if I stretched it out more? Would that do it? Oh well, I can't think of one where it's exclusively due to the functions themselves, but I can think of one where they're not necessarily functions, but they're equations, in which case they can loop around. So if I did something like, okay, you probably won't encounter this, but yeah, let's cross this out. Let's ignore this. But let's say you had, you'll probably never have to deal with a situation like this, but let's say you have something that does this, a region that does something like this, together with another region that does, how do I want to do this? Say a region that does this. Yeah, it's probably not the best example, but if I wanted to calculate this area over here, then I wouldn't really have a choice. I'd have to split it into multiple integrals, because over here you've got, if I do it as top curve minus bottom curve, you've got navy blue minus green, but then over here it's navy blue minus another part of the navy blue, but then over here it becomes navy blue minus green again, and then one more region of green minus green. So that's if I did it in the with respect to x. If I did it with respect to y, still a problem that needs splitting, because if you do it with respect to y, you would have, you'd have this section over here, which would be this navy blue minus this green, plus, well, there's also, within those same bounds, there's also another part over here that's green minus the navy blue. So yeah, the point is you can come up with regions. It's possible to come up with regions where neither doing it in the x direction nor doing it in the y direction will be simple, and you can't avoid splitting it. There's another case where it doesn't even have to do with what the graphs are necessarily. It just has to do with what area they want you to calculate. So you could have something like, this, where they give you two functions, so that's f of x and that's g of x, and you have to split this into two integrals to get the area between them, because for this part, the pink is above the orange, f of x is above g of x, but after you reach this intersection point, for this other part, g of x is above f of x. So for this one, you'd have to do an integral of f of x minus g of x first, and then plus your other integral. You need a separate integral because it changes to g of x minus f of x after that point. And that you are likely to encounter. I would imagine you've already seen scenarios like that if your teacher did a good job providing you with examples. Let me see. Where do we go from here? I guess we continue with applications. I'd rather get something ready for this section and see if it works first before I actually dive into this. Discs, washers, and cross sections. Yeah, I think I'm gonna wait on this. So I think this is a good place to call it a day for now. I'll come back after testing something out that I might be able to use for illustration if it actually works the way I'm expecting it to work. So I'll play around with that and see how well it works. And we'll just have that as part of the plan for our next stream, which will probably be on Friday evening. If not Friday evening, then sometime over the weekend. I'm flipping through the book, seeing if there's anything else of note that should be mentioned now, or if it should just be saved until next time. Okay, yeah, so volumes are for next time, and next time is where I'm probably going to start digging into stuff from Calc BC. So if you're doing Calc BC, then probably the next stream will have more things that are relevant to you. I mean, technically, all of this is relevant to you if you're in Calc BC, because you have to do the same things that AB does and then some, but you know, in case you're not having a problem with that first half and you're more concerned about the second half, we'll start digging deeper into that next time. And I guess for the Calc AB students, that's where you're going to start seeing stuff that is not going to be on your AP exam, so don't stress about it, but feel free to watch if you're curious. I'm not going to teach it all to you from the ground up, but if you're curious and you want to sort of preview what's to come, if you plan on doing BC next year, or you're graduating and doing Calc 2 in college, it doesn't hurt to preview. So yeah, I think that'll be it for today. So I'll figure out whether I'll be able to do this on Friday or sometime over the weekend, and I'll schedule it once I figure out what time would work. And yeah, so I will see you in the next stream. Take care, and I guess I hope this was helpful.